Alright, so today's lesson is on related rates. This is section 4.1. 3.8 video has already been posted. We're going to do this one now. We'll do 4.2 in class next week and maybe make a couple of adjustments as time goes on. So related rates are all about things that as one thing changes, it affects something else. Okay, so you can do a variety of things, but some of the classics that show up in this deal always are, suppose you have a ladder leaning against a building and the ladder is, a convenient length, 10 feet tall or something. And it is sliding away from the wall at 2 feet per second. How fast is it coming down the wall? So a couple of things. First of all, clearly that actually I'm going to call that y. Clearly that y feet per second is negative because it's coming down the wall. Okay, that's obvious. But the relationship here is its Pythagorean theorem. So x squared plus y squared is 10 squared. That's the relationship. And x and y are related to each other via this equation. So if I take the derivative of x, here's the key. Each of the x's and the y's are functions of t. So when you take the derivative of x, you're really saying you're taking the derivative of x with respect to t. So it's 2x dx dt. It's very much like a chain rule. Plus 2y dy dt equals 0, because of course that's a constant. Now, I don't know this fellow. Let's just say this is dy dt. But wait a minute. Well, this is dx dt, isn't it? Yeah, baby. It sure is. So you're like, okay, cool, I'll plug in numbers. Oh, crap. Well, I don't know what x is. Every single one of these problems, they're going to have to tell you, hey, look, find dy dt when what? When the foot of the ladder, let's say, is 6 feet from building. And you're like, well, what difference does that make? Well, it's going to change. As it gets further out, the rate at which y comes down is going to differ. So if this is 6, well, how am I going to find y? Well, again, Pythagorean theorem, that's going to make this guy 8. So 2 times 6 times 2, because this is positive because it's growing, x is getting bigger, plus 2 times 8 times dy dt. Now when I solve this, I'm going to get 16 dy dt equals negative 24. dy dt is equal to negative 1.5 feet per second. Ta-da! Some other ones that come up, this is a pretty classic. Oh, look, it's a cone. How exciting. And the cone is 5 feet high. You thought it was a paper cone, didn't you? And it has a radius of 3 feet. Sure. So you would agree that as you put water in, let's say water in, you are changing the volume. That is, you have some dV dt. And that's probably constant, probably. You're putting in, you're holding it to the tap on the sink and it's putting in at 3 gallons per minute or whatever. It's probably a pretty constant rate at which it's going in. But what's happening? Well, probably what you notice is the water level, this H right here, is changing too. Now, it's true that dr dt is also changing. It's also changing, but I don't really recall when I cared about that. I usually care about H because H is going to tell me when this thing's going to overflow. So, a couple things come to mind. Well, first of all, volume of cone, 1/3 pi r squared H. That's the first thing that comes to mind. Okay, well, we just said that dr dt, probably not important. So, there's got to be a reason for why it's not important. And the reason is because I have similar triangles. And so I know 3 over 5 is equal to r over h. Yes? Because I have a triangle here, and a big triangle all the way up to here, and they are both right triangles, and they're similar. So r is 3/5 of h, which means that I could rewrite this equation as 1/3 pi 3/5 h squared times h, or if you prefer, 1/3 pi 9/25 h cubed, or one more time, 3/25 pi h cubed. Ta-da! And now that I've rewritten it as v as a function of only h, then dv dt is equal to 3 over 25 pi times 3h squared dh dt. So, that's 9/25. I'm just going to clean this up a little bit. There you go. This is a true statement. Okay. So now, what are you going to ask me? Well, you're going to say, hey, look, when the tub is, 2 feet deep, or the water level is 2 feet deep, how fast is the level coming up? So, I don't know. Now, we say it's constant. The book's going to have to tell you. So, it's 5 cubic feet per minute. Okay, it can't really be in gallons. It could be in gallons, but you need to convert it to feet, right? Because all of this business over here is in feet per second, so it needs to be in feet per second as well. Now, this is simply a matter of doing some arithmetic here. Oh, here's my calculator. Oh, for God's sakes, pay attention to what you're doing. About 1.1. Of course, that would be feet per second. Would be my dH dt. How do I know it's feet? Well, because think about this here. This is in feet squared. These are constants. This is cubic feet. So you're going to have 5 cubic feet per second divided by square feet, and you're going to end up with feet per second. The units have to check. If they do not check, we have issues, obviously. Okay. Somewhere along the line, I've made this video about 10 times, and it very much annoys me that I keep losing this video. As much as I like this material, I get tired of teaching the same video every time. So, I'm going to just do a litany of all the possible video of these guys. So what I've drawn here, this is Sheriff Andy Taylor's patrol car back in 1950s Mayberry. Look it up on YouTube's there. But anyway, he had the old gumball machine light on top that would go around like so. You could also think of this very similar to a lighthouse. Anyway, if this thing is spinning at something like, I don't know, 20 RPM, that's revolutions per minute, that's 40 pi radians per minute. And maybe I want it in minutes per, when I want it per second, so that'd be 2 pi over 3, right, radians per second if I divide out by 60, okay? And so whatever, there it goes. Now, he has parked a certain distance from the building. Let's say he's parked 100 meters from the building. Okay? And let's say that it's spinning this direction, okay? So, at some point the light is going to be shining over to here somewhere. And it's going to be moving across the wall like so. Now notice the 100's not changing this time. This side is, but I'm not really sure I care about this side. And that has nothing to do with this guy right here. This thing has to do with this angle theta in here. Okay? So theta, how is theta related to this far side and 100? Well, the tangent of theta is x over 100, alright? So if I wanted to see how fast theta is changing, well, that screams take derivatives. So secant squared theta d theta dt is equal to 1 over 100 dx dt. Okay? So then the question then becomes, well, all right, so now I need to decide. Well, this is when x is negative on this side, I guess, and I'll say that's positive x is on this side, and this is 0 here. So when I say it's over here, let's say over here 40 feet, I'm going to plug in x equals negative 40. But you're like, wait a minute, that doesn't even make sense, Jay. Well, it does and it doesn't. But listen, if it's going across the wall this way, that means dx dt is positive all the way across. It was negative, it's going to 0, and then it was 0, and it's going to keep getting positive. So the big deal is this. We need that to be there. Because you'll notice down here there is no place where x is equal to anything. So down here we're going to solve for how fast it's moving across the building. But we need to know, you see, my nose. We need to know about x, so 40, in order to find out what theta is. So the arc tangent of 40 over 100. Now, should I put negative in there or not? You know, I wouldn't. I'm not sure that I would or wouldn't yet. We'll decide that in a second. I think I'm going to. If I plug that in, what you're going to see is that doesn't really make any difference what I get there. So I take the arctan of negative 40 divided by 100, and I get like negative 0.38 or something. Now I'm going to take the secant of that. So of course that means I'm going to take the cosine of it. Okay, well that's going to be a positive number. I take that to the negative 1 power, so I flip it over, and then I square whatever I get that this is 1.16. So what you see is it doesn't really make any difference, okay, whether it was positive or negative for that aspect, okay? But in a minute you're going to see where you're going to see. I just want you to think through these things as we do them. This is 2 pi over 3, and then of course multiply over here by 100. And you're going to end up with dx dt is this thing. So times 100 times 2 pi divided by 3. And I get 242.95 meters per second. Okay? Holy buckets, that's moving. Yeah, it is. No, it really is. This is right here 120 degrees every second. So that's moving right around. So it's not going to take very long to go across there. Okay, but notice it's always positive. Okay, now it's always positive, but is it going to be speeding up or slowing down? It's going to depend on this number right here. Well, what did this number depend on? This number depended on where on the wall it was over here. Notice if it was closer to 0. If it was closer to 0 right there, right, then this would be, let's say, closer to 0. So let's say 1. So this number is going to be very close to 0. Okay? What's the cosecant? What's the cosine of 0? It's 1 exactly. So a minute ago I had like 1.07 or something. Now I'm going to get 1. Okay? So when you flip it over and square it, it's still 1. So it's going to change based on where you are along the wall. And you could just pick a bunch of random numbers, you know, out here 200 feet or something, meters rather. So lots of fun on those guys. Do the same thing when it comes to a what do you call it, a lighthouse. So lots of different ways you can do it. Okay. Hey, an airplane is buzzing along. 1,000 feet of let's say 1,000 feet of elevation. Sure. And I'm over here. That's cool. And I am, I don't know, 10,000 feet away from it. Sure. And yeah. It's a terrible drawing. Right, whatever. I'd like to know how far this distance between us is changing. That's what I'd like to know. Well, if you look at this triangle, there are two sides of this triangle that are going to change. Okay? 1,000 is going to stay constant. That means it's going to stay in level flight, buzzing along like so. Wait a minute, he's buzzing along like so. Well, that gives me a, let's say, I don't know, a dz/dt or something, right? That is, he's got some kind of speed. And let's say that is 200 feet a second or something. I don't know. Just pulled that out of my fanny. There you go. But wait a minute. This is a change in this bottom side. So this bottom side must be z, okay? And maybe I started out at 10,000 feet away. But maybe as I come in a ways, what's going to happen, the airplane's going to be in here somewhere. Still at 1,000 feet of elevation, you see. But that this bottom side down here will have changed too, and so on and whatnot. You know, we can just see these different pieces and how they fit together. Clearly, it's going to be a Pythagorean theorem deal again. Okay, oops, I'm sorry, where this is still 1,000 meters or feet. So, if I can move my stupid board, I would do it. So x squared is going to be equal to 1,000 squared plus z squared. True that? So 2x dx dt is going to be equal to 2z dz dt. Lose the 2's because they look stupid. So I'm interested in, okay, maybe initially I was out here somewhere, and then maybe later on I'm at 10,000 feet in. Okay? Or, well, let's say 5,000 feet. That's a sucky picture. Let's do 500 feet this way. There we go. So when z is 500, you see, okay, and I know what dz dt is. Is it positive or is it negative 200? Well, it was out here somewhere, and as time has gone on, it's gotten smaller. So that's going to be negative 200. Okay. Oh, well, I need to solve for dx dt, so I need an x. Well, that x is going to come out of this business right here. And so if I plug in my values, that's 1,000 squared plus 500 squared to the 0.5, 11, 1118. And so if you divide that over there, 500 times 200 divided by 1118 is negative 89. So the plane is getting closer to me at a rate of negative 89 feet per second on that diagonal. Okay. Notice what else is changing. Hey, this angle is also changing, isn't it? Okay. So another way I could do this problem, or something else I could do with this problem, is to say, well, let's see, I got 1,000 over here. This bottom side is changing. Well, we called it z last time. Let's keep it z. Okay? But another thing that's changing this side right here. Well, hey, that's opposite and adjacent again, so we have ourselves a tangent problem again. So the tangent of theta is 1,000 over z. That's pretty cute. So secant squared theta d theta dt is equal to, now the derivative of z here is going to be negative 1,000 over z squared dz dt. If we were to use the same numbers as last time, that is, what happens when z is 500, okay, then let's see what happens here. Okay, so a couple things can happen here, by the way. A couple things. So I could, for instance, take the arctangent of, it's 1,000 over 500, so the arctangent of 2 is 1.107 in radians, and then take the cosine of that, and then flip that over, and then square that sucker, and you can get 5 right here, which is kind of cute. This whole thing is 5. D theta dt maybe is what I want to solve for, and then again this is going to be negative 1,000 over z over 5, sorry, over 5 500 squared. And then be careful because this is negative 200. Now we know this angle's increasing, so d theta dt better be positive. If it's not, you screwed up. So just make sure you get that right. So d theta dt 0.16 radians per second is increasing. Okay, at that time. Now another way to do this is to plug in the 500 right here. Use Pythagorean theorem to find the hippopotamus over there. So it's 1000 squared plus 500 squared. So this is the square root of 1250000 whatever. And if you can do the which is 500 square root of 5. Okay. Now what's the cosine of this guy? Well, I'm sorry, I want the secant. So the secant would be 500 root 5 over 500. So then when you square that, you get 5. That's another way to get that number right there. So if you're on a deserted island, don't have your calculator with you, you could always sketch a little triangle in the sand and go to town with it. It's pretty easy to do there in that regard. So yeah. So if you have this problem, and I really like this problem a lot, the resistors in parallel, right? Just a total resistance. So obviously the total resistance is going to change as you change the resistors that are in parallel, obviously. Duh. So there's R1 and R2. The total resistance is just, if you treat that as if it's a package deal. So what I'm looking for is the RDT, that is how fast it's changing. But obviously that's going to be affected by the change in R1 and a change in R2, right? So in other words, it's going to be a function of both of those guys, right? So I don't think anybody's shocked by that. So what's the derivative of this side? Well, it's going to be negative 1 over RT squared dRT dt d little t for time is equal to, and of course this is the same thing except with R1s everywhere. Sometimes you'll see me write this one. That's a force of habit from Calc 4. We do partial derivatives, and they're similar critters, but they they're similar critters, but they there's a little different story there, basically. So clearly, if I know initially that this is 5 ohms and 10 ohms, then I can find RT right off the bat. So it's 1/5 plus 1/10, which would be 2/10, which would be 3/10. So this would RT would be something like 3.333. And again, this is just will be given to you obviously in the problem, right? And then I'm going to tell you how much I'm changing this thing. Well, if I'm increasing that by, like in 1 ohm per second, and I'm decreasing this one by 2 ohms per second. Ooh. In other words, I am changing the resistances. In one, I'm making it bigger. In one, I'm making it smaller. Hey, what's the net result there? So when I do this, I'm going to take negative 2 divided by 25 minus 1/100th. That's Q. And then I'm going to divide it by negative 1 divided by 3.333 squared. And the answer is basically 10. If I hadn't rounded it off, that's what I would have gotten. And so the total resistance is increasing by 10 ohms every second. Yay! And the crowd goes wild. Okay. It's a pretty sweet deal there. These are pretty neat deals, just and because of how they work with one another. It's kind of a neat deal. How they all how all these different pieces and parts come into play there. Okay. You could also do this. Here's Romeo and Juliet, star-crossed lovers that they are. So I'm leaving you, Juliet. I'm going this way. Oh, okay. So here's Romeo, and he's moving along this route at I don't know, 6 miles an hour. I guess he's running. He doesn't like her very much, and she's going this way at 8 miles an hour. She didn't like him. She likes him even less. So good for her. Okay. And let's see. They both leave at noon. So how fast is the distance between them changing at 1 p.m. Okay? 1 p.m. Let's say, I guess we'll do 1 p.m. then we'll change it up in a second, do 2 p.m. or something. Well, again, sure looks like this is a Pythagorean theorem if you prefer distance formula. I'm going to do it this way for something different if you don't mind. And that's d squared. Okay. You could use the distance formula here. I don't particularly like the distance formula. First of all, I know it's just Pythagorean theorem for idiots. But second of all, it adds that extra hardness of now I've got to take a derivative. It's automatically it's a chain rule because it's the square root of a bunch of crap inside of it. I don't want to do that. So this is going to be 2r dr dt plus 2j dj dt plus equals 2d dd dt. Now, by the way, notice this is important. This is very important. Okay? Before we had a constant here or here somewhere. Here they're all three changing. So it's fine. Just be aware of that. So at 1 o'clock, Romeo is 6 miles away. Right? And she is 8 miles away. And so 2 times, oh geez, what's D? Well, it turns out D is 10. Again, because of that relationship, right? And so there you have it. So it'd be 72 plus 128, 197. Oops, no it's not. It's 200. Divided by 20 is, so it's 10. So dd dt is 10. Okay? 10 what? Well, 10 miles an hour. Okay? Now, well, wait a minute. What if Juliet, he leaves at noon, so he leaves at noon, still 6 miles an hour, but she waits until 1 to leave. I don't know. Okay? 8 miles an hour still. Okay? At 3 p.m., how fast is the distance changing? Okay? Well, I don't know. Well, but I do. It's basically the same deal. So if she leaves till 1, she's walked for 2 hours. This side is going to be 16. This side's going to be 18 because he walked for the full 3 hours. So this side is still Pythagorean theorem. Oh, for God's sakes, what did you do now? Nope. Maybe if you put a plus sign between them, you moron. Not a time. Didn't understand why I got such a big freaking number. Ah! Stop it! Stop it! Stop it! About 24. So D would be 24-ish. Right? There you go. So this formula up here is the same exact formula, so there's no point in recreating the wheel. Romeo is 18 away now, but moving at 6. She is 16 away. Still moving at 8 though. And now they are 24 apart. So of course it's going to be a different answer this time, but the process is still the same. .83. And of course, again, it is positive because of the fact that they're moving away. The distance is obviously going to be increasing. Okay? Those are basically the problems that you're going to be looking at. They're all pretty straightforward. Just, pay attention here. They're both moving away. If Romeo was here, oh, Romeo, or Juliet rather, and oh, Romeo, but for whatever reason they don't go across here as a marsh or something, I don't know. They're both moving in, then this, D Juliet dt would obviously be negative, and so would dr dt would be negative because that's getting smaller, right? One could be getting smaller, and one could be, no, I don't like you, Juliet, I'm going away from you. Okay. Then this guy could be positive. So just pay attention to that, and make sure you keep track of who's positive and who's negative. This is one place where positive and negatives make a huge difference. So just be aware of that.